Okay, welcome all of you. Thanks for coming. Let me talk about the plan today. So I'm going to share my desktop so that we can see what's going on. Okay, so the plan today is that we will start with Q&A. If there's any questions, as always, and not just start with it, but I'm always happy to answer questions throughout. Then today is actually, I'd like to say it's the big day in terms of what this course is all about. So from today on, we're going to be doing hypothesis testing. Hypothesis testing is the most important thing that is done in statistics for making decisions. Whereas confidence intervals are great for just getting an estimate of things, but hypothesis testing is what's happening when you have to make a decision, which is really important. So we'll look at the system or the step-by-step process of hypothesis testing. And it's funny thing is you've all seen hypothesis testing because it is a standard thing you learn in, I believe, 7th grade. Okay, but you hear it under a different name called the scientific method, but it's the same thing. So you've all heard of the scientific method. You may not remember it because you were in 7th grade or so, but it's the same thing. Is you start out with your idea, which in statistics, we're going to call the null and alternative hypotheses. And then what you do is you analyze what could go wrong, and that's called a type 1 error and a type 2 error. And then you decide on the level of significance, which is kind of it's very similar to the confidence level. It's kind of upside down though, it turns out. Confidence level is all about, you want to be 99% chance you're right. In terms of level of significance, for some reason, and I have no idea why, it talks about the chance you're wrong. So people go for wrong instead of right with hypothesis testing. Again, don't shoot the messenger on this. I'm just doing what everyone does. Then we'll get into the p-value, and that's going to be using everything we've been doing in terms of the calculations in statistics, where you're going to have a normal curve, and you're going to be looking at the area under a normal curve of being as rare as what you got, and that's called the p-value. Okay, as rare or rarer, it turns out. Then we'll talk about how do you state the conclusion. So just like when we stated a conclusion for hypothesis testing, for confidence intervals, we would say with 95% confident, the population mean or proportion is whatever. So similarly, there's going to be a way to state your conclusion in a hypothesis test. We'll also look at the p-value and realize it's a probability, and how do you kind of talk about that probability. Also, the level of significance. Remember, there's a chance you're wrong, but it's a little more complicated than that. We'll talk about what is that level of significance. And just let you know, this week, we're going to be dealing with quantitative data. So that means you have a number answer. And we're also going to deal with the yes, no question. So that's this week, and it's going to be a single survey question. Okay, then I'll give you some ideas about project 2 and how to plan for it. It turns out you're not really ready for project 2 until next week. So instead of just spending a whole hour just talking about project 2, I like to kind of talk about a little bit each week. But next week will be the bigger week for it, because next week you'll actually have the mathematics that you need to be able to really get an idea. But as you might guess, project 2 is going to involve confidence intervals, which was last week, and hypothesis testing, which is this week, but in a format that involves next week. So that's why next week is when we'll really be ready. So that is the plan. I want to open it up. Are there any questions about anything?
Is there going to be a survey for project 2 that we need to eventually do and gather data for?
That's a good question. The answer is maybe. I know that's not what you expected. It's very different than project 1. Project 1, it was an absolute requirement. You're going to have to, you had to ask people or email people a survey. For project 2, it turns out you have to collect data. And that doesn't have to be asking people. So collecting data literally could be, you know, measuring heights of trees if you want. Okay, and just like in project 1, you're going to have to do more than 30. So if you're going to measure heights of trees, you got to measure 31 trees. Does that make sense? But it doesn't have to be a survey. And you're not going to have to do, project 1 was all about survey techniques and preventing bias. So project 2 is not about that. So if there's bias, that's fine. You can do convenience sampling. And I'm saying that's fine for project 2. It's not fine for the real world. So when you get out of this class, and let's say you want to, you know, do a research project for your upper division or master's level psychology class, convenience sampling is not okay. But for project 2, I'm letting it happen as long as you admit to it. You don't lose points for it. Okay, does that totally answer your question?
Yeah, I have another question about confidence level.
Mm-hmm.
It's like we had some questions on the assignment that was like increased confidence level equals an increased margin of error when the standard deviation and the sample size doesn't change.
Mm-hmm.
Why? I couldn't get my head around it conceptually.
Okay, so it's kind of a give or take. If you want to be 99.999% confident, then you're not going to be able to get a narrow range to be that confident.
Oh, you know what? I get it.
So if I want to go to 99.99% confident on height, for example, I may have to go between, you know, an average height of adults. So I might have to go between 4 feet and 10 feet. Do you see that? But if I'm okay with only being 90% confident, I could probably then say, you know, 5'6" and 5'8" or something like that.
Okay, my next question is, how does the sample size relate to the confidence level, the margin of error, and all of that stuff?
Right. So that's the big thing about that is central limit theorem. You may not have been thinking about it, but the standard error based on the central limit theorem has a square root of the sample size in the denominator. So if you raise the sample size, you decrease the standard error. So if you decrease the standard error, you also decrease the margin of error. Because it turns out the margin of error is just the standard error times a number. Like if you're using 95%, it's just times 2. So if you decrease the standard error, then you decrease the margin of error, and you decrease the standard error by increasing the sample size because of that root n on the denominator. Does that make some sense?
So raise sample size, decrease standard error.
Yeah, right. But you know, everything's a give and take. If you raise the sample size, that means you have a lot more work to do. Right? If I told you had to do a survey of 300 people for your project instead of, you know, 31, it would have been a much harder project, right? So again, there's always, you know, give and take in terms of, you know, the things you can do to change things. So
I'm sorry, one more time. What is the difference between standard error and margin? Wait, margin of error is confidence level. Standard error is sampling distribution.
Okay, so it kind of comes from it. So the standard error is the standard deviation of the sampling distribution. And if you're doing means, it's sigma over square root of n. If you're doing proportions, it's p times 1 minus p over n, take the square root of all of that. So that was the standard error, standard deviation of the sampling distribution. The margin of error brings in that confidence level. So it's how far out you have to go from your sample mean or proportion so that when you look at the normal curve, it covers, let's say, 95%. If you want a 95% confidence level. So the standard error for a 95% confidence level is how far out you have to go from the sample mean and proportion to get 0.95 as your area under the curve. Does that make sense? And it turns out from, you know, kind of math is that the margin of error is a multiple of the standard error. sometimes a messy multiple, right? Like 1.96 if you want to go 2 decimal places for 99% confidence, or 645 if you want to go for a 90%. So depending on the percent confidence level, it's going to be a different multiple of the standard error. Does that make some sense?
Oh.
Yeah, so a lot of math involved. Okay, good questions though, really good questions. Okay, and we'll be talking about a little today, actually. Any other questions? Okay, if there's no questions, and by the way, today's a pretty deep day, just to let you know that. Is a deep day. This hypothesis testing is very deep. The good news is that if you don't understand all of it this week, we redo it next week and the week after and the week after that and the week after that. So hopefully by the end of the quarter, you better understand hypothesis testing, because that's pretty much all we're doing for the rest of the class is hypothesis testing. So I want to, let you know. Okay, so in the hypothesis testing, it's a step-by-step process. And I want to do it by example, something that you've been totally asleep the last couple of years if you've never heard of COVID. So I want to talk about, to me, the most important hypothesis test that has happened in the last at least 10 years, maybe much, much longer. And that is the vaccination. Okay, I don't know if you thought about it, but the FDA has to approve the vaccination, right? How do they decide to approve the vaccination? Any thoughts?
Don't they do like those massive trials?
Right, they do. So they do a trial. Okay. And the first thing that you have to do is say, well, what are we looking for? And I'm giving, by the way, this is depending on like the year you're looking at, the time you're looking at. Let's suppose that right now, 4%, or not right now, sorry, pre-vaccination. Let's say 4% of the population got COVID. Got it? So it's about right in those days. Okay, so I'm giving you a little history of the vaccination, but to me, I think that was like, it was on everyone's mind, and it should still be on your mind a bit. So the first thing you do is you say, well, if 4% of people are getting COVID, okay, there's pre-vaccination, then we want to make sure that after you get vaccinated, you have a much smaller chance of getting COVID, right? If you still have a 4% chance of getting COVID, okay, and by the way, we could say getting COVID or dying of COVID. It really depends on what you're concerned about. I'm just making life easy for us. We're just going to call it getting COVID. Sounds okay? Because they're pretty different. But let's suppose you had a 4% chance of getting COVID before the vaccination. So the hope is after the vaccination, what do you hope your percent's going to be?
0.
Well, you can hope it's going to be 0, but in terms of medicine, that never works.
Less than 4%.
Yeah, you hope it's less than 4%. You hope the vaccination actually does something. Because if you have a less than 4% chance of getting COVID, if you're vaccinated, and if you're not vaccinated, you have a 4% chance of getting COVID, then you want to get vaccinated. Is that clear? Okay. And I do want to let you know it's very complex. And I'm doing one small piece of the whole vaccination experiment, but I did read through all of it because I was interested, and hopefully you're interested in that kind of stuff too, to make sure it's safe and all that kind of stuff. So we're not talking about safety and all that. We're just talking about getting COVID versus not getting COVID. So what you do is you come up with what's called a null hypothesis and an alternative hypothesis. So the symbols, and the symbols are very important, and you have to know the symbols. The symbol for the null hypothesis, we use capital H as the abbreviation for the word hypothesis. And then we use a sub-0. And the bad news is the British got to it before the Americans got to it. You know what the British call 0? Null. Huh? Yeah, null. Yeah, so So not, they call it not. So we call it, so you'll hear me say H not because the British call it not. Okay. And again, they got to it before we got to it, so we have to live with it. It's their language. So it's H not, and it's an H sub 0. And then it's a colon. And this is important, by the way, because a lot of people make mistakes. It is not an equal sign right here. So this is going to be in just about everything we do for the rest of the course is going to have the symbol H sub 0 colon. Any questions on that? I will let you know, it is a pain in the butt to type this thing in Canvas. So if you're doing, or my math, you may not realize you're in it, but if you're doing my open math, you are welcome to use like a little subscript button, which is, you know, underline or kind of shift just above the P thing. And that will give you a little underline 0. So I'm not picky on making it pretty. I will be for project 2, by the way, because project 2, you have lots of time, you get help and all that. But for like your exam, week 8 exam, for example, it's fine if you can, you know, just explain what you're writing. Okay. Then here, just like confidence intervals, we're talking about a yes/no question. What are you going to ask the person? Let's say, you know, 3 months after they got the vaccination, what are you going to ask that person?
Did you get COVID?
Exactly. Did you get COVID? And the person is either going to say yes, or the person is going to say no. So just like confidence intervals, when it's a yes/no question, we use the letter P, P for proportion.
But don't they have to expose everybody to COVID to make it like fair, or else? Because what if you just get the vaccine and then
Okay, so
your house?
this is actually next week. So again, as I mentioned, it's a lot more complicated than what I'm talking about.
Okay, yeah, I'll just.
So what they do is they did a randomized control study. So what they do is they give literally, they had 40,000 people. So N was 40,000, at which 20,000 of them got the COVID shot. The other 20,000 of them got what they thought was the COVID shot, but was actually a shot with nothing in it. And then what they did is they compared the two. Okay, now next week we're going to talk about that type of testing. So again, I can't get into the details, you know, and I'll never get into all the details that they did, but that's what they did for this particular test. And that's what we'll talk about next week with this randomized control, and we'll have some different symbols. I'm trying to keep it easy though.
Yeah, I
Does
got
that
you.
make sense though?
Oh yeah. I just you're
Yeah. And that's how it was done. Okay. I don't know anyone who was in the experiment, but I know they did it. I read a lot about it. Okay. So with H naught, always gonna have an equal sign. So P equals, and then 0.04 in our case, because if nothing works, if the vaccination doesn't work, then you can have a 4% chance of getting COVID, right? So that's H naught. H naught is kind of what you're trying to show is not correct. H1 is going to be what you're trying to show is correct. Okay, so sometimes I'll call the H naught the status quo. Status quo is, it doesn't do anything.
So since it's a yes/no question, the first part of that is the no, and the second part is the yes.
Actually, it has nothing to do with being a yes/no question, but it was a good question. The yes/no question tells you have a P right here.
Okay.
Being so there's a yes/no question is what you're going to ask the individual person. Did you get COVID? The other yes/no is the proportion of people who got COVID after vaccination less than 0.04? And when you have a yes/no about the proportion of a population, that means is hypothesis testing. Okay, and that could be for a mean of the population, and it'll be hypothesis testing. Does that make sense?
Not yet, but it will.
Okay, so we'll get there. We'll get there. We'll get there when we see a mean. I'll do a mean example also. Mean as in like average, not being evil or anything. So the null hypothesis is this H naught. Then we have the alternative hypothesis. And I want to let you know, give you a heads up. You'll actually see two things given for alternative hypotheses. So this example has an H sub 1. Sometimes you'll see H sub A. Okay, and they both show up. You'll see them both. So I want to give you a heads up that that could happen. Okay, so H naught or HA, you choose A for alternative, by the way, or 1 because it's the number after 0. You get to choose. Colon, and then we still have a P because it's still a proportion of people who got COVID. But now it's what we're trying to show. We're trying to show is that the proportion of people who are vaccinated who got COVID is less than 4%. Any questions on that? Any questions? Okay, so that's the null hypothesis and alternative hypothesis. By the way, what I am telling you is a step-by-step process. Step 1 is to write down the null and alternative hypothesis based on your idea. And your idea is the vaccine works. Do you see that? So that's step 1. Okay. Oops, that should be a 2. Step 2 is interesting. Step 2 is to see what could go wrong. And it turns out there's always 2 things that could go wrong. And when I talk about going wrong, I mean, if you do everything right, something can still go wrong. Remember, with confidence intervals, if you do everything right, are you always going to have the population mean, for example, in the interval for a confidence interval?
No.
No. Sometimes you're going to get unlucky. Does that make sense? Okay. Similarly, with hypothesis tests, sometimes you're going to get unlucky, right? Maybe you're going to, randomly choose 10,000 people and you just got weird luck, and those 10,000 people are like just people who love going to bars and taking cruises and stuff like that, but not on purpose. You just randomly happen, and they tend to get COVID a lot. Does that make sense? And that could happen. Okay. So the idea is you want to say, well, what bad things, what can go wrong? And the 2 things that go wrong, we're going to call the first one a type 1 error. Okay, and what that is we reject the null hypothesis when the null hypothesis is true. Okay, so in this case, let's type out what that means for COVID, for this COVID thing. So if we reject the null hypothesis, we say that the null hypothesis is wrong. H naught's wrong, which means H1 is correct. And if H1 is correct, what are we going to do? So if the FDA decides, based on their testing, that H1 is correct, then what's going to happen?
They'll pass the vaccine.
Yep, they're gonna pass the vaccine, right? Accept the vaccination. They're going to encourage everyone in the world to take it. And what's going to happen?
They'll get COVID less than 4% of the time.
Yeah, the vaccine or equal 4%, actually. So the idea is H1 naught was correct, but you decided it wasn't.
Oh, you're talking about the type 1 error.
This is a type 1 error. So a type 1 error in terms of the,
they approve the vaccine and then give it to everybody, and 4% still get COVID.
yeah. So the ramifications is everyone,
Gets COVID still.
yeah, not everyone gets COVID, only 4% get COVID still.
4%.
But everyone gets vaccinated. But the vaccine is useless. Okay, the vaccine is useless. So some of the ramifications might be that people think that they are safe.
More people get COVID.
Yeah, I just wrote the vaccine is useless. I didn't write everyone gets COVID, but the vaccine is useless. So people think that they're safe, all right, safer, and end up getting COVID anyway. Okay, not everyone gets COVID, but the vaccine didn't do anything, and you know that's so. Is that a good thing, by the way? No, errors are always bad. Just let you know that. That's why it's an error. Okay, this is pretty bad, isn't it? Okay, now there's a type 2 error. Type 2 error is that there is not enough evidence to reject the null hypothesis. We say we fail to reject the null hypothesis. Okay, when the null hypothesis was false. So in other words, in this case, H0 is false, H1 is true. So if everyone gets vaccinated, the proportion of people who get COVID would go down, be less than 4%. But we don't have evidence to say that that's true. And if there's not evidence to say it's true, what's going to happen?
The FDA won't pass it.
Right, the FDA won't approve the vaccination. So the FDA does not approve the vaccine, but the vaccine works. Okay, so we're not allowed to get vaccinated. Okay, people die of COVID when the vaccine would have prevented death. Is that good?
No.
No, that's bad too, right? Which is worse?
Probably type 2.
I think type 2 is worse. I think type 2 is worse. That the which is worse is very much a opinion type thing.
Objective.
But my feeling is that it's worth if people are dying. Okay. But you might feel that it's worse if you have to get vaccinated when you don't want to. But I think it's worse when you die. That's just my opinion. And again, I'm not here to tell you about it, which opinion should be right, but you should be able to at least write a paragraph or whatever, a couple sentences on your reasoning. Does that make sense? Okay, I want to mention one thing that's important. Notice the terminology here. There's not enough evidence to reject. We fail to reject. Okay. Whereas the other with rejecting is you accept H1. You never accept H0, it turns out. You never accept P equals 0.04. Because the idea is you can't know exactly 0.04. It might be, say, 0.039999, right? Really close to 0.04, but may not have been exactly, and you're not going to be able to detect that in any sample. Does that make sense?
Wait, can you say that one more time?
Okay, so in the hypothesis testing conclusion, you either say that H1 is true, or you end up saying we don't have evidence to show H1 is true, but you don't say H0 is true.
Okay.
That's how hypothesis testing works. Okay, and I'll talk about this, not just today, but next week and the week after we'll explain. I'll explain more. But it has to do with the fact that you don't know, you can't get an exact equality.
But
You
even if
can't
they
know.
even if they do the testing and they give people the vaccine, and when they give it, this 4% of the people get COVID, the null hypothesis is still not true.
Only if you gave it to the entire population. And then it's not a hypothesis, it's just a known. Do you see?
Okay. So if you do your 40,000 vaccines and 4% get it, it's still not true.
Right, because who knows what the other 340 million people would do. Does that make sense?
Yeah. So in that case, there is just not enough evidence to reject the null hypothesis.
Exactly. Okay.
Like
And
a
the,
negative, it's not
and the
really.
reasoning is if you end up not having the evidence, then it means one of two things. One, either P was 0.04, or maybe your sample size is just too small and you weren't able to get the evidence. But you never know. You never know if your sample size is too small. So that's all you can say is you just do a very fancy way of saying, I don't know.
Right.
That's all this is. There is not enough evidence to reject the null hypothesis when the null hypothesis is false, or so if you fail to reject, then you would say, we don't have enough evidence to state that the proportion of people who get vaccinated and end up with COVID is less than 4%. That's a very fancy way of saying, I really don't know anything about this vaccine. But I do want you to learn the fancy language.
Can you just say those one more time? H of naught is P. How do you say that?
So in words, it's null hypothesis is the population proportion is equal to 4% or 0.04. In symbols, you would say H naught, P equals 0.04.
H naught, P equals 0.4. Okay. And then the other one's H1 or HA.
Yeah. Good questions, though. Good questions. Okay, so once you have dealt with your type, you looked at your type 1 and type 2 error. By the way, this must be in order, by the way. Okay, you can't, first thing, there's no way you can know the type 1 and type 2 error ideas if you don't have an idea in the first place. Do you agree? So obviously the idea has to come first. Like, hey, maybe the vaccine works. If you didn't even say that, you can't even talk about it. So the next thing you do is decide about the type 1 to type 2 errors. And then you decide on a level of significance.
All this is before you do the testing.
Right, haven't done any testing. This is just all in your imagination.
You're just figuring out where things could go wrong before
You're
you
just
do it.
hoping if it works, yeah. Yeah, we haven't even tested yet. Okay, we'll get to the testing. But before you do the testing, even after the type 1 and 2 type 2 error, writing down, is one more thing you have to do, and that is decide on the level of significance, which must be done before you test. So in our class, and it's kind of standard, it's not me being weird, 5% is a standard level of significance. So the idea is if the ramifications of a type 1 and type 2 error balance each other out, or basically, the one's not worse than the other, then use 5%. And that, again, the other side of the coin is the confidence level. What was the confidence level that was the standard?
95.
95. So confidence level was the chance of being right. Level of significance is the chance of being wrong. So that's why we use 95%. Okay. But let you know that the confidence, if you're doing a big study, you're doing both a hypothesis test and the confidence interval, you don't have to have, if you have a 95% confidence level, you don't have to choose a 5% level of significance because they're decided for different reasons. So just a note, it's a mistake a lot of people make on their project. Okay, so you decide on the level of significance. So if it's if the type 1 error and the type 2 error are basically just as bad, go for 5%.
What do you mean just as bad?
There's a lot of times when you look at the ramifications or what damage is done because of type 1 error, and you look at what damage is done because of a type 2 error. And if that damage for the type 1 error is just as bad as the damage for type 2 error, go for the 5%. Does that make sense?
Okay.
Not yet, but I think that if you give us an example later on, it would make sense.
Yeah, we'll get different examples. We'll definitely have different examples, but I can't do all the examples at once. So I'm going through one example and then we'll do other examples, I promise. Okay.
So just one other question can I ask real quick? This level of significance, 5%, does that mean kind of that there's a 5% chance that there will be a type 1 or type 2 error, or not at all?
Yeah, let me be more specific though. There's a 5% chance that there's a type 1 error.
Oh, okay, only type 1.
Yeah, and the reasoning behind it's too hard for this class.
Oh, okay. So
Just let you know, the type 2 error.
no,
is really
that's fine.
complicated.
If you say that, I just go with it. So
Yeah, you
only
just go with
type-
that. And if you don't want to go with it, you need to change your major and become a statistics major.
I just go with it. I
Yeah.
don't question it.
There's a lot of fancy stuff in this class that I have to just say.
Okay,
I
so
don't
if
know
type
the-
1 and type 2 error are about equally as bad, there's a 5% chance.
Not there's a 5% chance, we're gonna choose 5%
Right, we're
for a level.
Choose 5% for only type 1 though.
Yeah. And that's called the level of significance. Okay. If the type 1 error is worse than the type 2 error, okay, then you're going to, instead of choosing a 5%, you're going to choose a 1%. Okay.
All right.
Because remember the standard error is the chance of a type 1 error. So if 1 is really bad, if the type 1 error is really bad, you want that percent to be smaller because you don't want it to happen. Does that make sense?
Okay, so if type 1 error is worse than type 2 error, then choose 1%.
Exactly.
If it's like type 1 error, everybody dies, and type 2 error, nobody dies, then 1%.
Wait, if you said if type 1 error, everyone dies, type 2 error, everyone dies,
Type 2 error,
then it's
nobody
5%. They're the same.
Nobody dies. Type 2 error, nobody dies.
Yeah, then you're going to go for the 1%. Okay. Yeah.
Okay.
Yeah. In the real world, actually, you're going to go 0.00001% if it's that bad. Does that make sense? But for our class, I'm just going to have 3 numbers that we're going to go for. In the real world, if it's that different, then you're going to change it a bit more. But again, I can only do so much in an elementary stats class.
No, I understand. I'm just trying to, yep, I get it.
Yeah.
Thank you.
Okay. On the other hand, if the type 2 error is worse than a type 1 error, then you can use 10%. Because it's a give and take. If you make the type 1 error a smaller probability, then you make the type 2 error a larger probability, and vice versa. So that's the give and take. Okay. And by the way, any guess on what's the only way to make both of them have a smaller probability? We've talked about this before lots of times.
Bigger sample size?
Yeah, bigger sample size. Bigger sample size. And just a note, if you have a biased sample, you can't do anything. It's just a joke. So if you have bias, it's a, if you have bad bias, then you shouldn't even do a hypothesis test. Basically, you don't do anything with bad bias. Okay, any questions so far? So what should we use for our particular, what should we use for our level of significance? You should know because we already talked about it.
1%.
Okay.
10%, 10%.
10%.
10%, because remember, with the type 2 error, people are dying. With the type 1 error, people have to go in and get a shot and nothing happens. Okay, they might have a little reaction. I got tired after my vaccination, but that's about it. And I'd rather get tired than die. How about you? Okay, I hope all of us would. So the idea is that type 2 error is worse. So since the type 2 error is worse, we're going to choose a 10%.
Wouldn't the same amount of people die in 1? Because if the vaccine doesn't work, it's the same as 2, where nobody gets vaccinated? No?
Okay, so if no one gets, so the idea is if you reject the null hypothesis, you can have fewer people dying. If it works. Do you see that?
Oh, you're assuming it still works.
Right, but if it
Oh,
doesn't work, and
Yeah, I thought you were saying the vaccine was useless in the type 1 error.
right, if the vaccine is useless, then you have the same number of people dying with the error. So that doesn't sound like any big deal at all, except that it costs a lot of money. You have to spend a day in bed because you're tired the next day. There's still some bad things. Do you see? It's just you don't have more people dying. Okay. And it turns out in the real world, you probably do have more people dying, because if people think the vaccine's working, they're probably going to be less careful.
Yeah, that's what I was saying. More
I'm not
people.
about you guys, but I'm definitely less careful than I was before I got my vaccination. Before I got my vaccination, I wouldn't go near anyone. When I was hiking, if I had to pass one, I'd hold my breath. Even if I was wearing a mask, I wouldn't even breathe for 10 seconds till I passed them. And I never heard anyone else do it, but that's guaranteed. You can't get it if you don't breathe. And it worked. And I have not gotten COVID, by the way.
We tested out that hypothesis.
Yeah. No, but they actually have looked at that with the breathing thing. Yeah, so, but that's another, you know, I can only say so much. So the next step is the hardest step of all, by the way, and that's collect the data. Okay, when you think about it, these first steps, they take 10 minutes, right? You have to come up with the idea. It might be 5 minutes even. That's no big deal. Collecting data, that's a lot of work. You gotta give 10,000 people the vaccination. You have to keep track of them. You have to survey them. That's a huge amount of work. So in the real world, you want to make sure that you don't make a mistake at the beginning, because you do not want to waste this step, the collect the data step. Any questions on that? Okay, so it's easy to say collect the data, but in the real world, that is hard. Any questions on that? Okay, and I want to let you know it was specifically hard and still hasn't been done for small children, like babies. They still don't have data for babies, it turns out. It's just not there. It's so hard. But even for adults, it was a lot of work. It took months and months to collect that data. Any questions on that? But it's easy to say, collect the data, but really hard to do. Okay, the next step is put the data in the computer and calculate the p-value. Okay, so let me explain what happens. So you are going to you collected your data, and let's suppose that you vaccinated 10,000 randomly selected people, and then you waited a few months, and at that few months, let's say 1% of them ended up getting COVID, okay, which is less than 4%. The problem is that you only looked at 10,000 people out of the 240 million Americans. Do you see that? So the good news is, if you looked at 10,000 people, then by the central limit theorem, you're guaranteed that the distribution of the sampling distribution is approximately normal. So we can draw this curve. Any questions on the curve? And
Okay, so that curve is representative of the sampling distribution of the 10,000, yes?
yes, that's a sampling distribution, okay? Okay, then what you do is you say, well, the mean of the sampling distribution is your hypothesized mean, which was 4%, 0.04. And let's suppose we ended up with 0.01, which sounds better, but is it better enough? Like, did you just was it just, random chance? Or is it very unlikely that it would be 4% and you would end up getting 1%? Does that make sense? So if you draw this picture, then to get 1% or less, because less is even better than that, right? Then that's the shaded area. Do you see the shaded area? That shaded area is called the p-value. And P stands for probability. Unfortunately, we use probability so much in statistics that the letter P is used a lot. So we call that the p-value. This is called a left-tailed test. I'm hoping you can all say, why is this called a left-tailed test?
Because you want the, because H1 would be lower than the mean.
Yeah, lower and lower side on a graph is the left side. Do you see that? I want to let you know that sometimes you do a right-tailed test. Not for this example, but let's suppose you want to find out if you make more money in a business if you, I don't know, let's say if you advertise. Then you'd be doing the right-tailed test. Because H1 would be that mu is greater than the mean that you've been doing without advertising. Do you see that? So that'd be a right-tailed test. There's one other type. Any guess?
Right in the middle?
Good try. But remember, you can never show that it's actually 0.04. You can never show that. The other one is a two-tailed test. An example of that, let me give you the medical example. Let's suppose you're doing blood pressure. You want to look, you want to show people are healthy, okay, and worry that if they do something bad, if they're stressed or something, they're going to get unhealthy. Then if you have blood pressure that's very low, is that good?
No,
How about if you have blood pressure that's very high? Is that good?
also no.
Right. So if you're going to do a test to find out if stress is making people unhealthy, then you may want to do a two-tailed test for that if you're doing blood pressure. Because if it's either too low or too high, then it's unhealthy. Do you see that? So that would be an example of a two-tailed test. Okay. Any questions on that? Okay, so here's the picture. And again, we've had this picture, pictures like this before. Normal distribution, we got area under a curve, etc. Okay, so just to note, the null hypothesis is what you're trying to refute. The alternative hypothesis is what you're hoping to find evidence that it is true. Okay, so in this case, by the way, what do you think the p-value ended up being for the test? And this is real, by the way. FDA did a test. Okay. And by the way, do you know where the original test was done? It's not a statistics question.
When?
Where?
Was it in Georgia?
Good try, but no. Should I tell you? Israel. So Israel was the first hypothesis test done for the Pfizer. For Pfizer. Just to let you know. So the first test was done at Pfizer. And the idea is for that test, any guess what the p-value was?
0.01.
About that, yeah. Pretty close, actually. So actually a little less than that. It was very small. It was about 0.004, if I remember right, something like that, somewhere in that range. So it was very small. And the p-value, huh?
They get people to sign up voluntarily to take it.
Oh yeah, you can't, right? But remember they did do that with what I call the randomized control study, which we'll get into next week. So they signed up voluntarily, but they didn't know if they were actually going to get the vaccine or get a placebo.
Okay.
So they signed up voluntarily, but they did a split group randomized control study. Okay, which is the best kind of studying, by the way. Okay, that's how it worked. Just let you know. And we'll be doing that next week. I'll get into the details of that next week, how those work. Okay, any questions on that? Okay, so when they had a p-value, if the p-value is very small, so let's say the p was equal to 0.004, which is certainly less than 0.1, because that was our number. The level of significance is that boundary at which if the p-value is less than the boundary, you say, yes, we can give the vaccine. I'm going to reject the null hypothesis, and I'm going to say the alternative hypothesis is true. I got statistically significant evidence. So let me write this down. I want to make it bigger because it's really important. You would say there is statistically significant evidence to conclude that the population proportion. So just like confidence intervals, you have to, in this class, specifically use that word population or all, but you have to specifically say that you're talking about everyone, not the sample. Vaccinated people who get COVID is less than 4%, 0.04. Okay, and I want to highlight a few things because they're always going to be used. Statistically significant evidence. So when you reject the null hypothesis, when you get a small p-value, use those words. And population. Always talking about that. Any questions on that? Okay. Just to note, and this drove me crazy, when they did the test for children under 18, okay, it was, I think, 12 to 18 years old. Do you remember that happening? So children weren't able to get the vaccination until after adults were. Do you remember that?
Yeah.
I read the study and the p-value was not less than 10%. I believe it was something like 12%. I'm like, what? I was pissed. Now we have much better studies and now we have a low p-value. Okay, so fortunately, you know, even though they pushed a little too fast, it didn't kill a bunch of children.
Hey, when you say 10% or 12%, are we measuring the difference between the mean and the p-value?
No, when I say 10%, when I said the p-value was 12%, that's that area under this curve here.
Wait, so that means kids that took the vaccine, 12% of them got COVID?
No, it doesn't mean that. It meant that there was a 12% chance of a type 1 error.
Oh, okay, gotcha.
Right now, it turned out there wasn't a type 1 error. Remember, 12% is still not that high, but it's higher than standard that you're supposed to let happen for those kind of things. Does that make sense? Yeah, I was shocked when I read the journal article and it's like, what?
I
It
do
happens
not.
sometimes.
Okay, so in this chart in front of us with a 0.01 and a 0.04,
Mhm.
how do we determine what the error is on that?
With them error. Well,
Like, is it 5%? Is it 10%? Like, how
okay,
do
so
I
the
know?
level of significance you decide on before you even collect your data. That's the first thing, remember? And it doesn't show on this chart. And the p-value is this area. And you might be able to guess how you're going to actually come up with that area.
You would have to get the standard deviation, right?
But I'm going to tell you how you are going to have to do it in one word.
With your calculator?
Yeah, the calculator. Yeah, so you can use a calculator. The math is really brutal, but you can trust me that I did it for you, okay? Okay, and by the way, if you didn't use my calculator, use someone else's, and this class would never have you do it by hand. Just let you know that. Okay, so whoever teaches it, wherever they are, you know, if everyone uses a calculator. Okay, does that make sense?
Yeah, did we already learn that function and I'm getting what it is?
Oh, we'll get there.
Okay.
We'll get there. Here comes the next one. I'm going to give you, there's a few functions I'm going to show you. Okay, so here's another one. This is, I don't remember any of you from Tahoe?
I've lived there a lot, but I live in Reno now.
Okay, so there's something called Snapshot Day, which is this Saturday. So I thought I'd bring something real. Our big thing is how healthy our water is in Tahoe, the lake. And one of the things that they measure, and they, by the way, I've done it every year, not as a statistician, just as a community volunteer. I've helped them with the stats, but that was a whole different thing. That's because they knew I was the stats guy. But usually I just do the fun stuff and do the measurements for them. Okay, and me and another 50 people or so, volunteers. You go out and test it and we look at the pH of streams that flow into Lake Tahoe. And one of the questions, and again, you don't have to know chemistry or even know what pH means, but if you happen to know it, you might know that pH of pure water is 7. So one question might be, does the average pH in streams that flow into Lake Tahoe differ from 7? Any questions on that? Okay, so the first thing you do is you write down your null and alternative hypotheses. So we're going to write H naught, mu, because now we're talking about a population mean, we're not talking about a proportion. Because I'm going to go out into a stream and I'm going to get a pH reader. I'm going to look at it and it's going to give me a number and it's going to say 7.2. And I'm going to write that on and send that to the researchers, to the ones that analyze. Does that make sense? There's no yes or no here. We measure the pH of all the different streams. Okay. And H1 is mu is not equal to 7. Okay. And whether you know it or not, I'm telling you, if you have pH that's far from 7, either like say 9 or 5, that's really bad for Lake Tahoe. It's a little like the health issue. You don't want pH very far from the pH of water. If it's a really low pH, it's acidic. You have acidic water, bad acid. And if you have really high pH, it's called basic, which is bad also in a different way. So again, I don't expect you to know the chemistry, but I was a chemistry minor, so I do know that stuff. But you can trust me. Any questions on this idea? Okay, so we're doing a two-tailed test because of this not equal to sign. Is that clear? Okay, now let's look at the type 1 and type 2 error. Remember, type 1 is you reject the null hypothesis when the null hypothesis is true. So in this case, what does that mean? What's going to happen? What are the ramifications? Ramification means bad stuff. That's an English word, not a stats word, by the way.
So I think that would mean that you think it's not 7, but it's 7. So you think it's bad, but it's actually good.
Mm-hmm. So you're going to spend a lot of money to mitigate a problem that is not even a problem, that doesn't exist. Right? We're going to spend all this time trying to make it back to 7, with however they decide to do it, with best management practices and rules and regulations and all kinds of stuff, zoning laws or whatever. But it wasn't even a problem because we just, it was a 7. Does that make sense?
Yeah,
Is that bad, by the way?
pretty bad.
That's pretty bad. Okay, now let's go to the type 2 error. Type 2 error, you fail to reject the null hypothesis when the alternative hypothesis is true. So what is
That's really
this?
bad.
That's really
That's
bad.
like-
And
So what's going to happen? What are the ramifications?
there'd be acidic or basic water flowing into Lake Tahoe and nobody would do anything about it.
Exactly. We have acidic or basic. Basic sounds good. Basic's bad, by the way. Water flowing in Lake Tahoe. Nothing gets done because we didn't know there was a problem. The ecosystem gets disturbed. The lake life dies. Does that make sense?
Yep.
Okay, so you have to decide which is worse.
Type 2 is worse.
Probably 2.
Okay, so if you think 2 is worse, again, a lot of it has to do with your political situation. That's why I'm gonna ask you guys. So if we think 2 is worse, then what should we use?
5%.
10%, right?
Yeah, so in this case, use a 10% level. Significance. Okay, so let's say we did the measurement, okay, and it hasn't happened yet because we're doing it on Saturday. It does happen every year, by the way. We did the measurement, and let's say that the measurement was X bar was 6.4, okay, and let's say the p-value turned out to be 0.27. Then that's greater than the 10%.
Wait, did we go over how to find the p-value yet, or?
Not
no?
yet. It turns out it's easy. I'll show you the calculator. It's easy. I promise.
Okay, there's a, okay.
There's a calculator for it. Okay. The hardest part is to know whether it's proportions or means, same as confidence intervals. Then you go to the right calculator and you just do it. Okay. So the p-value, let's say, was 0.27. So by the way, here's the chart. Notice, by the way, that the hypothesized mean was 7. Our sample mean was 6.4. How did I get to 7.6?
We went
Because
margin of
it's,
error the other way. I don't know if that's the right wording, but
Yeah, because 6.7 minus 6.4 is 0.6. Right? 6.4 is 0.6 to the left of 7. So if I want to find out what the number is over here, I add that difference, the 7 minus 6.4, the 0.6, to 7, and I get 7.6. Any questions on that? And you are responsible to know how to do that, because that's something that I don't consider like really brutal calculation wise. Do you think so?
no, but why is that number significant?
Because in the picture, take a look.
That's what gives you the two tails.
Yep, we got the two tails. And it's going to be part of our analysis. So first thing, if our p-value is 0.27, that means that the total combined two areas here is 0.27 because it's two tails. It's the area of both tails combined. So now we can say there is statistically insignificant evidence. Okay, notice the other one was significant. It doesn't change much. You got to put that IN in front. To make a conclusion about whether the pH or the population mean pH of inflow into Lake Tahoe exceeds, differs from 7.0. Any questions? I want to highlight statistically insignificant evidence. So that's the big difference with this example. Any questions on this conclusion here? Okay, here's another example. Now I can give you more data. Okay, suppose you want to see if women are not drinking the recommended 2.7 liters per day on average. Okay, I don't know if you know, but you're supposed to drink on average. You know, the medical people tell you you're supposed to drink, 2.7 liters a day for women. Okay. So H naught is mu is 0.27. And if women aren't drinking enough, then H1 is mu is less than 2.7. Okay. By the way, if you drink a little more, that's fine. You just got to pee a little more, but that's okay. Health-wise, it's okay. But if you don't drink enough, that's where you have health issues in terms of the medical stuff. Any questions on this so far?
Just out of curiosity, if you change that question to do you drink 2.7 liters a day, then that would be a proportion, correct? Because then it would be a yes, no.
Yeah, that was a survey question.
Okay.
Right. But I gave you data, which I made up, by the way, but I gave you data. So let's suppose we decided on a 0.01 level significance. Again, I can't get into all the details on every one because we'll run out of time. But hopefully we've talked about level significance already and all that. You do a type 1, type 2 error. Now I'm going to show you the calculator. Okay, so what you can do is I'm going to copy this stuff. Okay, by the way, when you do the exam, okay, you can do the copy and paste just like I did too. I always put, usually put commas in. And then we're going to go to the calculator. And do I have it right here? Thought I had that. No, I'll make it. There it is. Any guess on what calculator we're going to use?
Number 14.
14 is a really good idea, except we
15.
don't have statistics, but we have
Oh.
data.
Yeah, we got that.
Yeah, so we're gonna do 15 because we have data. Okay, so I'm gonna go to 15. We have a mean we're looking at because it was a mu. We have data. And just like you've done before, when there's data, you copy and paste or you type in with commas between all the data. Okay. Then what we do, wait a minute. Yeah, it says, then type in the population standard deviation if it's known, or leave it blank if it's not known. Do we know the population standard deviation?
No,
No, so leave it blank. Do we have a less than, do we have a greater than, or do we have a not equal to?
less than, right?
I thought it was a not equal to 7.
We're on this one now. It's a less than.
Sorry.
Yeah, that's a less than. So I make sure I click on less than. Mu naught. That's always that's the mean number in H naught. So the mean number in H naught is 2.7. And then I hit calculate.
Is that a 2.7 or an at least than 2.7? And does that make a difference?
So in terms of the 2.7, that just comes from H naught. That's why I put a naught there, mu naught, because it's the mu for H naught.
Okay.
Yeah. So the less than was important, but that was important right here. Does that make sense?
Yeah, I got it.
Okay. All right. So just a note, this is, we don't know the standard deviation of the population. So this uses the student's t just like we did with confidence intervals. Do you remember that? And it gives you, by the way, the sample mean, it gives you the sample standard deviation. It gives you, this is called the test statistic. And that's like the value if you adjust for the mean and standard deviation. I'll just keep it there. Okay, so if they ask you for the test statistic, in this case, it's t equals this big ugly number. The p-value is 0.03. Let me put that in because that's our most important number. Any questions on that?
I missed, what was the test statistics again?
So the test statistic is what happens if you you adjust for the mean and standard deviation. It's kind of like, it's a lot like, remember the z-score?
Wait, is this the student T?
Yeah, it's like the standard t.
Okay, never mind. That's
Yeah.
all. I got confused.
Yeah, it's a lot like the z-score, but since we're dealing with the student's t distribution, it's a t-score.
I
So
got
we
it.
can see negative 1.9, it's close to an outlier, but not quite there yet. Do you see that?
Yeah.
Okay. So we have a 0.03. By the way, if we're using a 0.01 level significance, we can say that is greater than 0.01. So then, and I want to show you the template. The template is there is statistically significant evidence to support the claim that the population, either mean or proportion, and then whatever you want to support the claim about. And the template for failing to reject is exactly the same thing with the IN there. Okay, so in our case, we had insignificant evidence because our p-value is big. To support the claim that the population, in this case, is it mean or proportion?
Mean.
Okay, and then those X's, don't leave the X's there, by the way. We need to change those. And it is, again, we're looking at the mean liters of water per day women drink. Is, and we want to show it was less than. Remember, we have insignificant evidence that it's less than 2.7 liters. Oops. Per day. Any questions on that?
Can I see the calculator one more time? The results?
Sure. And if we're using a level of significance of 0.01 and the p-value is bigger than 0.01.
And that's why it's statistically insignificant, right?
Exactly. That's why it's statistically insignificant instead of significant.
Okay, I got it.
If it was a greater than sign and the numbers were the same, it would be statistically significant, correct?
When you say it was a grade, not this guy, right?
Yeah.
This guy is not about statistically significant. It's whether this number here is less than or greater than the level of significance, which was 1%.
Oh, okay. It has nothing to do with the
No.
original.
If I change greater than, you're going to get a very different p-value, 0.97,
Okay.
which would make sense because if you ended up with a mean of 2.54, you're not going to say that it was greater than 2.7 no matter what. You see that?
Right.
Yeah, so that's why. Okay, so let's continue on. Okay, let's interpret the p-value. So here's a template. And it is if the null hypothesis is true, but you need to change that null hypothesis is true to talk about the null hypothesis. And another sample, I should say of, whatever your sample size was taken, then there would be whatever the probability we got, whatever your p-value was, probability that the results of the new study would be at least as extreme as results of this study. So in our case, we would say if, now the null hypothesis was true, that would mean the population mean amount of water women drink was 1.7 liters per day. Okay, then we say, and another sample of. And our sample size was, I don't know if it had it here. No, I'll have to count. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Let's say 33. Not 100% sure, but I think it was 33. So, and another sample of 33 women were surveyed. Then there would be and our p-value here, remember, was 0.03. So a 3% chance that the sample mean for the new survey would be and then what we got again, that's over here, 2.54. liters per day or less.
Shouldn't that first not be 2.7 at 1 point?
Oh yeah, 2.7, thanks. That was a typo. Any questions on interpreting the p-value? Okay, now let's interpret the level of significance. It helps to copy and paste the p-value interpretation and adjust. So the level of significance template starts the same. If the null hypothesis is true and another sample of whatever was taken, then there would be A, and then it would be the level of significance probability that the new study would result in falsely concluding that the alternative hypothesis is true. So now let's write that out. And I'm going to copy and paste the beginning. It starts the same. If the population mean amount of water women drink was 2.7 liters per day, and another sample of 33 women were surveyed, then there would be A, and now I got to change the rest. Now we're doing a 1% level of significance, 1% chance that the result of the new study would lead us to falsely conclude that the population mean amount of water women drink is less than 2.7 liters per day. So it's basically, it is the probability of a type 1 error. Any questions? I'll let you look at that for a second. Any questions on that? Okay, let's do another example. And here it is. Are the majority of Americans against a mask mandate on airplanes? What do you think?
Probably.
No.
Yeah. So we got to know. So how do we find out?
Survey.
Yep. So let's do it. But before you survey, let's follow the steps. So we have H naught, and that is P equals 0.5, because remember the smallest percent that could happen that isn't the majority is 50%. Is that clear?
Yep.
Okay. Whereas if you're above the majority, that doesn't mean you're at least 51%. Does that make sense?
Yep.
Yes.
Let me give you an example, a personal example of that. I might have done this, I might have told you this one before already, but I'll tell you my personal example. When I ran for election for a school board in my first election, I got the majority of votes, but it was 50.02%. But I won because that was above 50%. Okay, that was pretty weird, wasn't it?
What was that, like one vote?
It was 3 votes.
Okay.
Yeah, 3 votes out of something like 14,000 or 13,000 people who voted. 3 votes more than the other candidate.
That's crazy. That's crazy
Yeah.
close.
Yeah, so, and that was that's true, by the way. That's a true story. Yeah, personal story. Okay, the good news is that it was all a happy election. We weren't like yelling and screaming at each other kind of stuff. It wasn't like you hear in national politics. It was much more subdued. Okay, so a majority means exactly 50%. And I mean, a majority means greater than 50% or greater than 0.5. Okay, by the way, is this a left tail test, a right tail test, or a 2-tail test?
Right?
Yeah, there's a right tail test because it's greater than. Any questions on this? Okay, now this is political science. Turns out in political science, okay, I'm sorry, this is kind of politics, right? in politics, what do you think you're going to use most of the time when it comes to the level of significance?
5%.
5%. 5% is standard, because if you look at type 1 and type 2 error, they both have issues, right? Type 1 error is you thought the majority agreed with it, and so then you decided, well, we're going to make everyone have masks, and guess what? More than 50% of the people are pissed at you, right? Okay, whereas the type 2 error is you weren't able to say that the majority agreed when the majority really did agree. And then then you're going to have more than 50% pissed at you because you're not going to have a mandate. Does that make sense? Either way, you can have more than half pissed at you. Okay, that's politics. So then what you do is you do your study. Any questions on that? And the ones that did the study was Gallup. And by the way, it says Americans divided on face masks when flying. Let's find out if that's really true. So it turns out that 51% feel it should not be mandated. And I'm going to spare you, I did my own research on reading this thing. And 51% is our p hat, because that's our sample proportion. The sample size I did was 3,995. If you read the bottom of the article, you'll see that. One thing you're going to need to do is figure out what your number of people that said yes. Yes means I'm against the mask mandate. How many there are. And let's get to that. So I'm going to go back to the calculator menu. Which number should I use?
16.
Exactly, 16, because this is a proportion question. The survey question is, do you think masks should be mandated on airplanes? And the person's going to say yes or no. Does that make sense? So it's a proportion question. We're doing a hypothesis test. It's a single proportion. I click on that. Our N was 3,995. X, we're going to do a little bit of work on this. So let's go to scientific calculator. And if you take 3,995 and multiply it by 51%, which is 0.51, you get about 2,037, always round in the nearest whole number. So 2,037. Our P naught, that was the H naught was P equals 0.5. So there's our P naught 0.5. We want to find out if P is greater than 0.5. So I click on the greater than sign. Any questions so far in the calculator? NA calculate. What do you say? Take a look. What's the conclusion?
I don't get the Z.
Okay, so Z, remember we're looking at, so for first thing you can quickly see that NP is 2,037, NQ is going to be 1,000 something, definitely bigger than 5. Is that clear? So the central limit theorem tells us that the distribution, the sampling distribution is approximately normal. When the sampling distribution is approximately normal, that means that we can use the normal distribution, and Z is the letter for the normal distribution. Do you remember that?
Yeah, but what's the 1.2498?
Okay, so we could look at that actually and say that's actually not that big. Remember, 2 is the outlier idea, right?
Okay.
So we could actually, even without looking at the p-value, we can kind of guess that the p-value is going to be pretty high. Do you see that?
Yeah.
So this is a z-score. And the z-score is about 1.2, which isn't that unusual, right? It's not that high.
Does that mean that the furthest data point out is 1.249 away from the mean, standard deviations away from the mean?
So remember, so we're looking at the 0.51 was our sample proportion.
Oh, I got it. So the furthest data point out.
Yeah, so if you look at
0.51,
0.51
okay.
compared to 0.5, right? Then that has a z-score of 1.2 or so. That's what that means.
So P is 0.10, which is greater than,
Yeah,
Right.
and just a note, and this is important, especially when you're doing the assignment, that including the exams. If you say 0.10, you got a problem. It's going to mark you wrong. How come?
4 decimal points normally.
Yeah, even if they said 2 decimal places, 0.10 is wrong. How come?
Because you didn't round up, or I didn't
Yeah.
round up.
So be very careful. I want to give you a heads up. The computer is not nice about rounding errors. So when in doubt, go at least 4 decimal places. And that would be 0.1057 on the computer. Does that make sense?
Yeah, definitely. I was just trying to
Yeah.
put it into words.
And make sure you use the rules of rounding. Okay, so in particular, P is 0.10, so that means we do not have statistically significant evidence to conclude that the majority of all Americans, okay, now it's all Americans, not our sample, the majority of all Americans agree with the mask mandate, okay? Because that's what we're saying. Sorry, not agree, against the mask mandate. Does that make sense? So that's the conclusion. Any questions on this example? Okay, we only have so much time. I have lots of examples ready. Yeah, question?
So we found that because 0.1, it was statistically insignificant, yes?
Yeah, 0.1, because we're using 0.05 as our level of significance.
I gotcha.
And it was again, our p-value was 0.11, for example, which is definitely bigger than 0.05. And if we're bigger than the level of significance for the p-value is bigger than the level of significance, you have insignificant, statistically insignificant evidence. Sometimes you'll also hear insufficient evidence. That's another word you'll hear. I should give you a heads up on that. Any questions at all on this example with proportions? I want to show you one more thing that's important for this, this week's discussion post. This week's discussion post, you're not allowed to use things like Gallup. This week's discussion post, you have to use a peer-reviewed journal article. And a good thing is that the library at Lake Tahoe Community College has free access to huge collection of peer-reviewed journal articles. Okay, and this is to get you ready for upper division, by the way, because you're going to have to deal with it. You know, you have to read peer-reviewed journal articles. So let me just
They
show.
are accessible online?
Yeah, I'm going to show you. That's where I am right now. So go to ltcc.edu. Scroll down. Used to be on the top. Now you have to scroll down. It's kind of a pain. Scroll down and click library. Then go and click find articles. Is that clear? Then click academic search complete, our largest multidisciplinary database. And then, question? Okay, and then do your search, something you might be interested. Let's say you're interested in nursing. So click nursing, click search. And one of the things I can't emphasize strongly enough how important hypothesis testing is. It's so important that there's a very good chance that the very first article you look at is going to have hypothesis test with a p-value. So if I click on this, I'm just randomly grabbing one. I click full PDF text. Prevalence, type, and reasons for missed nursing care in municipality healthcare in Sweden, a cross-sectional study. And if I read through this, under data analysis, see anything important?
The p-values right
is
there,
less than or
less than or
Yeah.
equal to.
0.5.
Yeah, and by the way, in journal articles, they usually actually write down that it's less than a number instead of what it is. Because that's, everyone understands if it's less than 0.05, then that's statistically significant under standard processes, right? So there we go. This had a p-value, and it also gives you all the information here and stuff like that, right? I'm not going to read the whole article for you, but so I want to let you know, here's what you can't do because it doesn't work. So I want to give you a big heads up. And for those who are watching this as a recorded webinar, make sure you listen. Do not copy and paste the link. Unfortunately, that doesn't work. Someone will click on a link and it'll not give you access. Instead, what you want to do is you want to say you found it in the LTCC library search and copy and paste the title. Does that make sense? And if you copy and paste the title, then someone can search for the whole title and they'll always get what they're looking for. Does that make sense?
Okay,
So do not copy and paste a link because the link doesn't work. It's frustrating, but that's just how it is. So I want to give a heads up for this week's assignment is copy paste the title, not the link. Okay. And in fact, if you go to my post, I always do a sample post, which you've probably seen. That's what I did. I wrote, here's an article I found on LTCC's library collection. The title is, and then I wrote, you can find the p-value in the results section. You do want to guide the person to where the p-value is because these articles are often 50 pages long and it's not fair to ask someone to read 50 pages of article. So guide them to where the p-value is. Okay. And I recommend before you post to make sure that you can answer your own question. Okay. Don't do it. Don't type it in, but put it on a piece of paper just to make sure it works. Any questions on that? Okay. So secret word. So the secret word is there. You know why it's there?
why?
The first word of the conclusion of hypothesis test is there. It gets you started. Does that make sense? So I made the secret
Okay.
word there because whenever you do a hypothesis test, you're going to go, there is statistically either significant or insignificant evidence. Does that make sense? So I want to emphasize it. Sometimes knowing the first word at least gets you started. So if I ever ask you to write down the conclusion, then your first word should be there. And that'll get you started so you don't make the mistake of starting with when you're talking about, say, the level of significance, and that was if. Any questions on that? Okay, I do want to talk about the project. I know we're a little past 1:30, but today I told you today was a bit more of an intense day than some other days. But I'm only going to talk about a little bit, and I'll talk about more next week. So if I go back home, actually, if I got a syllabus, even better. We're now in projects, and we're in project 2. So the first thing about project 2 is it has the same partner rules as project 1. So what I recommend you all do, if you liked your partners, contact them, make sure that they liked you, and make sure they're still in the class, because we did have a few drops. So make sure that your partner's still in the class because you have to find partners. 3 is better than 2 if you can, because you have less work to do because you only have to do a third of it instead of half. And also if something happens and your partner drops out, you still have 1 left. So I recommend 3 if you can. And I did notice that on the project 2 discussion board, somebody already posted that they're looking for a partner. So, you know, if there's only 2 of you, please accept that person. Okay. And if I click on project 2, I'm not going to read all this because that's next week, but I'm going to let you know that the main things you're going to have to do in project 2 are a confidence interval and a hypothesis test. Okay, those are the 2 big things for the project. Any questions on that? Okay, I'm going to get into it in more detail next week because it's going to be a confidence interval for the difference between 2 population means. And that's what next week is all about, is differences when we have 2 samples. So that's just a note. So, you know, you can read through this, but you're really not ready to get started until next week. What you can get started with is make sure you have your partners. Is that clear? So next week I'll get into the details. And again, there's gonna be some things similar. You're gonna have a fictitious client that is gonna pay you in theory for your project. And then you're going to collect data. As I said at the very beginning, is that data collection is it's not the same mandates as project 1. That could be done just by grabbing numbers from something, you know what I mean? You could look at, you know, weather in New York versus weather in Los Angeles. Look at the high temperatures and see which is warmer or something. I don't know. If you have a good reason for it. Okay. What the processes are the same though. Step 1 is partners. Get your partners. Okay. Step 2. Do you remember after getting your partners what your step 2 was for project 1? I know it's been a while.
Collect the data.
Nope. Before you collected your data.
I think
You
it's
need
like
to do
decide
ID.
on your client and decide on what the question will be, right?
Yeah. So you decided on your idea and posted it on your project 1 discussion board. Do you remember that? So same idea for project 2. You're going to decide on your, not idea this case, you're going to decide on your hypothesis. And you're going to post your hypothesis on the project 1 discussion board. Is that clear? I'm sorry, project 2 discussion board in this case. This is project 2. So you're going to post your idea on the project 2 discussion board. Is that clear? Okay, that'll be step 2. Okay, and then I'll look at it and let you know if it's going to work. And then you're going to go through the process of hypothesis testing that we talked about today. You have your hypothesis that's been posted on the project 2 discussion board. Then you're going to decide what are the ramifications of a type 1 and type 2 error. And then you're going to decide based on that what the level of significance should be. And then you're going to collect your data. Okay, and again, that could be going to a market and looking at prices, or it could be looking at weather reports, or it could be asking people a survey question, taking measurements, whatever it takes. You're going to have sample sizes, and that we'll talk about next week, why I'm making it plural, of over 30. And then after you've collected your data, then you're going to do the full analysis of your data. And I'll talk more about that next time because we don't quite have the information about hypothesis tests and confidence intervals for comparing 2 different things. And that's next week. And that's what the project will be about. So you're not quite ready for, you know, posting on the discussion board. That you need to hear next week's stuff first. But you are definitely ready for partners. Okay. And then after you, you know, write down your draft, you send me the draft. I'll give you lots of comments and then fix the comments. You can, again, post on the project 2 discussion board. You can go ask Braulio for help, and he's always happy to help you on that. You can come to my office hours, and that, you know, virtually is fine, and I can help you too. Okay, and then the date is a while from now, by the way, but I figured I might as well talk about it. So June 19th. So you have 33 days from today. Just let you know. So you have a while to do this. That's why you don't have to stress out right now. But next week is when you should get started. This week you should get your partners. Any questions at all about just the ideas for project 2, not the details, not ready for those yet. Okay, what I'm going to do is I'm going to stop my share and stop the recording.